Was I going to start? Oh, yeah. Let's go through the results for the game. All right, so we're through round 8. Here are the latest standings. Not really a lot of change. Nobody moved more than one spot up or down, except for CD's racks. They dropped 2 spots into dead last. Okay, here's the sales versus price data for this round. We now see many prices below $20 a unit. And this is compared to previous periods. Oops. So again, the blue dots are the most recent periods. So prices are pretty low, not terribly different from the previous period, but still edging slightly downward. It's kind of interesting to see how the prices have progressed throughout the course of the game, starting, I don't know, in the $55 range and ending up more in the $25 range. And I always find it very interesting. And I always find that the exact same thing happens every year. All right, so here are the assets by period. So what we see is 3 groups that are way behind, and then a whole bunch of groups that are right in the mix. All right, it's still pretty close. So anything could happen there. Stock prices are all over the place. In fact, they seem to have regressed to the mean, sort of. The highest are just above 21. The lowest are above 17. So not a whole lot of variation in stock price, surprisingly. Let's look at the industry report. Iraq is pretty much out of cash. On the other hand, the CD's racks is swimming in cash. I think we all remember why that was, because they just sold every single share of their own stock, which is why the value of their equity holdings is very low. Sitting on cash, not sure what they're up to, but I guess we'll probably find out. Finished goods inventory. So CD's nuts and bolts only has about $4,500 worth. Rack and roll 75. Those are the 2 lowest. Whereas these groups here have close to $90,000 in finished goods. And we sort of went over stock prices already. Again, notice that CD's racks has now liquidated all of their stock. Somehow not managing to crater their own stock price, at least not yet. Here are the sales from the previous period. Iraq had very low sales. Every other team was somewhere in the vicinity of 10,000, I believe these are units, 10,000 units. So everybody's selling except Iraq. Does anybody have any questions?
Are there 3 periods left or 4?
That was round 8, so there'll be 12 periods.
There 4 more?
4 more. Any other questions? All right, so since you sort of asked, damn it.
Tomorrow is the deadline for the decisions and screenshots for the next period.
I know, I'm just going to put that up. Except I messed something up here. There we go. So these are the lecture notes for today, but the first part of these lecture notes contains the schedule. So that's where you find them, is in today's lecture. All right, so this is today. Today we have the pleasure of talking about quality. Then tomorrow, your round 9 decisions are due. Then next Monday, your round 10 decisions are due. Then Wednesday, we'll have class as usual. And the following Monday, your decision 11 will be due. Now note that that's Thanksgiving week. So you will be home or on your way home or something. So if you want to finish them before you leave or over Zoom or however you want to do it, you got to do it. But remember that the Monday of Thanksgiving week, your decision, your round 11 decisions are available. And during Thanksgiving week, we will obviously have no class on Wednesday. Then the following Monday after Thanksgiving, the final period 12 decisions are due. Then the last day of class, we'll have final presentations. And the last assignment will be due. All right, so on the last day of class, we're going to have final presentations. So we will it'll probably take at least 2 hours, 2.5 hours to get through all of them, right? So I warned you at the beginning that we wouldn't go the whole class period except on the last day of class. Just be ready for that. And the presentations, well, the order of presentations, we'll start with the last place team. We'll give the first presentation and I'll work our way down to the first place team giving the final last presentation. I could make this bigger, couldn't I? All right, what is in this presentation? So make it 10 or 15 minutes. 10 minutes probably be better. And then maybe some questions from anybody, but mainly Cecile or myself. So here's what I'd like you to include in your presentations. Tell us what strategies you used, which strategies worked well for you, which strategies went wrong for you. Also comment and show the analytics that you use to help you make business decisions. After all, that's the topic of this class. If you were making all your decisions by picking numbers out of the air, then, well, you're going to have a hard time with this section. What tools did you develop? Which ones were most useful? And then last, comment on if you had to start this game all over, right? Like if I flunk you and you have to take it next year, what would you change knowing what you know now? How would you change your strategy? What else would you do knowing what you know now? All right, so that is basically what we're going to do for the rest of this class. Does anybody have any questions? Okay. Oops, gosh darn it. That being the case, we'll just press ahead. So now this is the topic for today. Quality in general, we're going to talk about kind of two sort of separate subjects, quality management and quality control. Quality control, statistical process control, there's sort of kind of quantitative tools used in process quality. I mean, they at least have a little bit of quantitative things in there, so that'll be okay when we finally get to that. But the first part is quality management. Me teaching management is perhaps a joke to start with. I will do my best. it is something I know about. It's just not something I'm very thrilled about. When I first started at Lehigh, I taught quality control. And this may surprise you, because I probably put you to sleep in this class, maybe, but I used to put myself to sleep when I used to teach this stuff. So, I mean, I do know the material, but not my favorite topic. All right, so we're starting with this quality management method. And I didn't tell you why I'm teaching this, is because I have to. The reason I have to is because you take this course, I've mentioned this before, because you take this course, you get to not take management, what is it? Supply chain management 180 something. In order to get that agreement with the business school, I have to teach certain topics, and this is one of them. All right. So there are several management philosophies, let's call them, in the area of quality. You may have heard of some of them. We've got down here, you got your Six Sigma, you've got your lean, total quality management, things like that. And from my perspective anyways, they've achieved almost a religious level in certain quarters, right? They're not all that different from each other, to be honest. I guess lean is arguably a little bit different. But basically, they're kind of all the same. We'll start with that. And then there's the statistical process control, which is a little bit more rigorous. We'll start with probably the oldest, total quality management. It's based on principles like this. See, this is what management, this is why I don't like teaching management. You have principles, right? So principles like measuring what the customer wants and needs. Meet or exceed customer expectations. Make everything fail-proof, fail-safe. Monitor your processes and use that information to improve the process. That's basically what statistical process control is. But it's, you know, just saying it is easy enough, but how do you actually do it is the better question. And benchmark with other companies, right? I'm sure your competitors will be happy to invite you in and share all of their trade secrets with you. Okay, so TQM, it's big on getting everyone in the organization to participate in this process improvement process. So there's sort of, it's like a cultural thing in many ways. So this whole idea, this history is a little bit interesting. There was a guy named W. Edwards Deming, who was an engineer for Bell Labs, and he actually worked in the Allentown plant, which still exists, right? If you ever go down Union Boulevard, or if you ever gone to an Iron Pigs game, it's right there. So he worked there, and for some reason moved to Japan and started selling is the wrong word, trying to spread his ideas for quality management. When I was your age, Japanese products were synonymous with the worst quality in the world. They were known for being of very poor quality, cheap, and all that. As you probably know now, the reputation of Japanese products is quite the opposite. And W. Edwards Deming is given credit for that by the Japanese people. In fact, there's something called the Deming Prize that's given out in Japan. It's probably the most prestigious corporate prize that they give. All right, so the history was interesting. The Japanese adopted his philosophy in a big way and turned around their whole country, their whole economy, you might argue. So Deming had 14 key points or principles, which I will list here and then talk about some of them. So you can kind of read through them. So one of them says cease dependence on inspection to achieve quality. So there was a time where you would achieve quality by inspecting everything you make and throwing away the bad crap. And he did not like that for at least two reasons. One reason was you don't always catch every mistake in an inspection. Inspection is not foolproof. But much more importantly, building stuff and then throwing it away is really expensive, right? This whole idea of inspecting quality into products used to exist, and you really don't hear that anymore. So Deming was also a big proponent of working with single suppliers. That a lot of people advocated this for a long time, and only recently have people started moving in the other direction, because there are some advantages for working with a single supplier, advantages of close partnership. But there are also disadvantages, or the risks. For example, if your supplier is mowed down by a hurricane or something like that. He's a big believer in constant improvement. I tend to agree with that. The way you get better is you slowly but surely, day after day, week after week, improve small things. And in the end, the end result is something very big. Looking for huge leaps forward, I mean, it happens from time to time, but usually it's lucky. Drive out fear. So that means that, employees should not be afraid to point out problems, in particular quality problems. And they should be part of the team rather than afraid to speak out. This is one of my favorites because I remember, well, I used to own a Ford Mustang back in the day when I was first a professor at Lehigh, and I remember parking in the parking lot, and this guy in a suit he's walking fast to catch up to me, and he says, "Hi, my name's so-and-so." I said, "I just want to apologize to you." And I said, why is that? And then he said, "I work for Ford." That's what a piece of crap my car was. And I remember at the time, the big advertisement on TV for Fords, they were filmed inside their plant, and they had these giant signs on the wall which said, "Quality is job one." So they put up a big sign. Don't think that really did a whole lot. So this one down here, basically you want everyone in the organization to understand about quality and understand about the process of improving quality, getting everybody to work together. So one of Deming's key points was that improving process quality reduces costs rather than increasing it. Okay, before Deming came along, people sort of believed that the way to improve the quality of products was to use more expensive raw materials, more expensive machines, and to inspect them very carefully so that you could weed out the bad units. Deming's idea was remarkably simple, and yet nobody really understood it till him, which is what you want to do is build it right the first time, right? It doesn't seem like an astounding observation now, but in its time, it really kind of was. Okay, so you don't hear about this much anymore. You more hear about Six Sigma and other stuff, but it's still used extensively in Europe, and honestly, it's not that much different from any of this other stuff anyways. Okay, continuous quality improvement, that was sort of, I don't know, the same idea, but with a different preacher. And it's based on sort of a feedback loop where you kind of monitor a process, learn about it, get information about it, try and figure out how to improve it, develop experiments, implement the results, and keep going, right? I mean, again, not an astounding idea. Okay, more recently, we heard about Six Sigma. This management philosophy was pioneered in General Electric and Motorola. How long ago was that? 25 years maybe? It's about reducing errors and process variability. It has sort of a top-down deployment with structured roles, and it uses this DMAIC stuff, which we'll get to. So, and why do they call it Six Sigma? So basically, you know, if you're talking, let's take a simple example. We're trying to make a nail that's 1 inch long, right? So when you make them, there's going to be variability from one nail to the next. And, you know, the actual length of the nails that you produce will follow some distribution. Now, beyond that, there are some specification limits, and the specification limits are supposed to indicate within what range the product is functional, right? So as long as the length of the nail is between these two limits, then the product is functional, right? Now, this picture is drawn so that this would, given the variance of this distribution, lower spec limit is 6 standard deviations from the mean, and the upper spec limit is 6 standard deviations from the mean. So the probability of producing any defective parts, that is parts outside of the spec limits, is essentially nil. That's why they call it Six Sigma. I'm not, but you know, that's really neither here nor there. Now, the whole idea though is that variation, process variation, is always bad. Here's another simple, maybe another example that will show you why it can also cost you money. This is just a picture of a bottle filling line. Bottle comes along, stick a tube in it, you turn the spigot for a certain amount of time, then you turn it off. Then you do it over and over again, and this is a process, and so you will not get exactly the same amount of soda in each bottle. There'll be some variation. On the other hand, the bottle's got a label on it that says 12 ounces. So if you don't put at least 12 ounces in there, you could get in big trouble, right? So you want to make sure you get 12 ounces in there. There's just sort of a picture to show the difference. So, so what you get to do is you get to set the mean amount of of soda in the bottle. So the red line represents our 12-ounce limit, right? We want to make sure that there are very, very, very few bottles represented by this small tail area down here that are underfilled, right? So in order to make sure this is a very small probability, the mean amount of soda we got to put in a bottle is going to be greater than 12 ounces, right? The same is true down here. The only difference is that this process has greater variability. So because it has greater variability, we have to set the mean higher in order to keep our underfill rate small. These big, thick double arrows represent how much free soda we're giving away because of the process variation, right? The process variation is bigger, we got to give away more free soda, which is costing us money. This is sort of a direct example of why process variation is the enemy and how it can cost you money. And I'm trying to think what to talk about here. All right, so I mean, the goal is to get as close to 0 defects as possible by reducing process variation. Now they've got this weird organizational structure set up where you have master black belts who teach the black belts, who teach the green belts, who teach the yellow belts. And we've got this top-down hierarchical management structure, which I find very strange. Very strange indeed. They have these two things, they're like acronyms, right? So this is how you improve a system: define, measure, analyze, improve, control. Okay, fine. Then they have their tools. So they have what they would consider to be statistical and graphical tools to help you improve quality. All right, so they have two kinds of different tools. One are tools, basically statistical tools to measure and display data, and methods for generating new ideas. So again, forgive me if my disdain shows through here, but so how do we generate new ideas? Let's take the what, why, where, when, who, how much approach, or 5W, 2H approach. Brainstorming, there's something I never heard of. Interviewing, talk to people. All right, so I mean, these are all kind of obvious things that I hope you already know to do. There are some weirder things that sociologist types get into, which would be, let's call this structured talking to people. Focus groups, not a bad idea. And again, benchmarking if you can do it. Ways to get ideas for how to improve things. And we have our quality circles, or as they're sometimes called, Kaizen teams, where you basically organize all the people in a department together for a meeting. And you talk about how to improve things. And maybe you teach them some of these tools so that they can, so they can use these tools to make things better. Here's some of the real fancy statistical techniques they propose. One is called a check sheet, or as I like to call it, counting. Histogram. It tells you which numbers are big and which numbers are small. This is the most sophisticated one they have. This is a scatter diagram, which shows the relationship between two variables. Flow chart. You may not have seen this. This is called a cause and effect diagram. It's just basically you identify an effect, which is like a quality defect. In this example, it's in a healthcare setting and the patient is waiting too long. And then you try and identify the causes of that negative effect that you then use these causes. Hopefully you can address them and make things better. Pareto diagram. So there's this kind of truism that 80% of the problems are caused by 20% of the causes. So you're trying to find, what's causing the biggest problem. And so rather than fixing the thing that's causing the smallest problem first, you finish the thing that's causing the biggest problem first. Got that? All right, lean. Now we're going on to the next one. This is lean, often called lean, comes from the Toyota production system. This one is slightly different. Oops. Telephone, sorry. Different. It's more of a bottoms-up approach. It is focused on continuous improvement and elimination of waste. And it does a lot of the same kind of team-based stuff that the other management philosophies use. And so they're using the teams to root out and eliminate waste and inefficiency. So one thing that they do is they look at a process and they try and map out value added and non-value added. So it's true that when you think about improving processes, you naturally think about the value added steps and trying to improve those. It's the natural thing to do. But what they're suggesting is you find all the non-value added activities and try and get rid of them because they're not adding any value. It reminded me, so basically what I like to call lean is, my name for lean is stop doing stupid stuff, right? And I was interested because I mentioned this to my colleague, Dr. Thiemann. Where is it? And he sent me an article. I gotta find it. So this is an article in the New England Journal of Medicine, which you can't see yet, I don't think. Now you can see it. New England Journal of Medicine. Getting rid of stupid stuff. Right? So I like that title a lot better. So in a nutshell, basically, that's what we're doing with all of these things, I might argue. And while I'm talking, nowhere in any sector of the economy or industry are they more in need of process and quality improvement than in medicine. The amount of waste, poor quality, inefficiency that goes on in the delivery of healthcare is unbelievable. If you haven't ever worked in an organization like that, you will be aghast at what goes on. Okay, so lean, so define customer value, value stream, make the value flow. I don't know what that means. One thing that they talk about is a pull rather than a push system, if you know what that means. If you imagine a sequential production process where you kind of do one step after another, what they'll do is they'll wait for an order and they'll start at the back, and the last step will basically order a product or a unit from the previous step, so it's pulled through rather than pushing stuff in, right? If you just keep pushing stuff through the system, you end up with lots of inventory, you end up with lots of work in process inventory in between steps, lots of finished goods inventory at the end. They would argue that all of this inventory floating around particular work in process tends to obscure a lot of the problems that are going on. If you can get rid of all of this inventory, you can usually more often see where the problems lie with your process. And they like to strive for excellence. I do too. I'm getting tired of talking about this crap. All right, so I guess the one good idea is try and find the non-value added steps and getting rid of them rather than focusing on the value added steps. Or, as they say, stop doing stupid stuff. Oh, I can't bring myself to say this or this or that. Well, this is not terribly important. All right, finally, we're on to something a little bit more quantitative. So this topic is called statistical process control. This is what the homework questions will be about. It's not rocket science by any means, but it is at least somewhat quantitative. All right, so it's based on the idea that all processes have variability. It's natural. And it's, you know, when the process is operating normally or as it's expected to, you will still see process variation. This is the kind of the natural random variation. And there can be non-random variation, right? Your process could be going along just fine and all of a sudden something goes wrong. The tool breaks, the machine breaks down, something happens, you get a bad batch of raw materials. Now you're seeing variation too, but that's not normal or natural, right? It has some systematic cause that's screwing everything up. And so in an ideal world, we would like to be able to detect the presence of this non-random variation and then do something about it. Think of it really as process monitoring, if you will. So they usually use control charts for this. So they'll take some measurements from the process and use that data to calculate statistics, which they plot over time on a control chart. And then also, in addition to the data on a control chart, you have upper and lower control limits. And the upper and lower control limits are meant to represent the range of natural variation, right? So if the process is going along like it's supposed to with only natural variation, it should stay pretty much between those control limits. So then the idea is if you see the process suddenly leave those control limits, you know that something must be wrong. That's the basic idea. Now, there's various kinds of measures. So there's various kinds of control charts. We're going to talk about, the first two we're going to talk about are called C charts and P charts. So C charts are for quality measures that are count type measures, like the number of defects on a sheet of steel, or the number of complaints submitted to the complaints department. Measurements of quality that are counts. P charts are for percentages or fractions. So here, if your measure of quality is the percentage of units that have defects or the percentage of customers that make complaints, then you would use a P chart for that kind of data. Okay, so we have count data. Just some more examples: defects on a wafer, medication errors in a week. And typically count data can be reasonably assumed to follow a Poisson distribution, which you all know from Math 231, I assume. And so when you need to establish these control limits on your chart, you can get the limits from the Poisson distribution. All right, so here's an example. We have, it looks like 24 2 years worth of data on the number of infections in an ICU. So 24 data points. And so these would be the data we'd plot on a chart over time. So you can imagine a chart with 24 points. We can find the average of all of these data. The average is 4. So hopefully you recall, if for a Poisson distribution, the mean and the variance are the same. So we're going to estimate the mean to be 4 by using the average. We can also estimate the standard deviation as being the square root of the average, since the variance and the mean are equal. And so we're going to take, the average is going to be the center line of our control chart. The upper control limit is going to be the average plus some multiple of the standard deviation. Some people use 2, some people use 3, plus, and then the other control limits will be minus, let's say 3 sigma. So the control limits are plus or minus 3 sigma from the average. All right, so I just created a chart from the data on the last page, and this is what it would look like, right? Here's our upper and lower control limits and our center line. And in this case, none of the data is plotting outside of the control limits. So it's telling us that in these 2 years worth of data, there's nothing that is seemingly unusual in what we're seeing there, all right? P charts are used for proportions. Proportion data is typically modeled with the binomial distribution. So if you recall, for a binomial distribution, well, it's based on the binomial distribution. It would actually, what we end up with the binomial random variable divided by n. But suffice it to say that, so, okay, this is the percent of the families that are dissatisfied. Here's the fraction. Oh, wait. Yeah, this should be the fraction over here. I don't think this is percent. But the point is you take the average, right? And that's an estimate of that. P bar is the average percent dissatisfied. Now the variance is given by P times 1 minus P divided by N, where N is the number surveyed. There are 200 families here, all right? So that gives us an estimate of the variance. Take the square root to get the standard deviation. And then plot your control limits at plus or minus, if you want, 2 standard deviations or 3 standard deviations, whichever you choose. So this is how you set up a P-chart, and in particular, how you set up the control limits for a P-chart. So I took that data right here and I plotted it. I set up the limits and I plotted it. Now this is important. These control limits are meant to represent, these control limits are meant to represent the range of natural variation, right? So if any of these data points come from a period of time when the process was not acting naturally, then they shouldn't be included in the calculation of the control limits. So if you set up your control chart like this and you say, oh, look at this, this thing is outside the control limits and this one here too. So when you're setting up your chart, you might throw these data points out and then only use the remaining data points and recalculate the control limits, right? So you get rid of those, take the remaining, recompute the control limits, and we would get obviously closer together control limits. What do we got next here? So the last control charts are for what are called variables measures, things that are measured in actual numbers, right? Not counts, not proportions, but actual numbers, like the length of something or the weight of something or whatever. So the way we do it is we typically take a sample of more than one, like we pull 5 shafts off of our production line and measure their diameter. So we have, did I say 10? We pull off 10 shafts and we have 10 data points. Then we take those 10 data points and we compute the average and the sample standard deviation based on those 10 data points. All right. So what we're going to do is we're going to create 2 charts. On one chart, we plot the average, X bar, and the other chart, we plot sample standard deviation, S. All right, so on an X bar chart, and hopefully this is a calculation that everyone knows well by now, but you know that the standard deviation of an average is S over the square root of N, right? So if we draw our control limits on our X bar chart at plus or minus 3S over the square root of N, that should allow us to monitor the mean of the process. I'm going to skip S charts for now. We're going to see that in our example. We're going to use a chi-square distribution to calculate the upper and lower control limits for our sample standard deviation. In fact, let's go to those examples right now. They're posted, obviously. All right, so this is just an example. So I have some proportion data here. Proportion out of 100 customers that were not satisfied. So basically, this is just data over, looks like 50 weeks, or 50 days, I'm sorry. So I just found the average of those data points. Then I took the average and I did P bar, the average, times 1 minus P bar divided by 100 square root. So that's the standard deviation of my statistic. And then I just take the average plus 3 sigma. I get the upper limit. And the average minus 3 sigma, get the lower limit. I plot my points on the chart and then I draw in the control lines, the upper and lower control limits. All of the points are inside the control limits, so we have successfully set up our P chart. And we can use it to monitor into the future the process. All right, and if we monitor in the future and all of a sudden there's a point way up here above the control limit, then we say, whoa, what's going on here? And you would go out, investigate, find the cause of the problem and fix it. Here's a C chart where we count the number of defects per unit on some product. There's our data. Just take the average. So we can use that as an estimate of the mean and as an estimate of the variance. Take the square root to get standard deviation. Then we do the mean plus 3 sigma to get an upper control limit. So this is count data, right? We really don't need a lower control limit per se. So I computed my upper control limit as V12.4. I plotted the data on the control chart. And this is what I got. All right. So when you look at the control chart, say, damn, something's wrong here. All right. Something has gone straight to hell here. I definitely don't want to set up my control chart including this data. So I'm going to get rid of this data, and I'm going to recompute the average and all of this stuff, including the upper control limit. So I recomputed it, and now I get this control limit, right? Again, this control limit was computed without this data, but now you can really clearly see that something has gone wrong here and it needs to be fixed. Okay, so the final ones are the X bar and R chart. I'm sorry, X bar and S chart. So in this case, I took 5 observations on some measure of quality. You can call it the diameter of a shaft if you want. And based on these 5 samples, I computed the average and the sample standard deviation. All right. So now I have a whole bunch of averages, one from each sample, right? So this is my data for the X bar chart. So I have to take the average of this column. Let's call that the average of averages, but it's just the average of column M. And I get my center line. Then I compute the average of my standard deviations, and that's going to be my estimate of S. And then, so I got it when I compute the standard error, remember that it's S over the square root of N. So I got to take my S and divide it by the square root of 5 because I have 5 data points. And then now this is my sigma. I'm going to go plus or minus 3 sigma. So it's going to be 10.59 plus 3 times 1.3 and then minus 3 times 1.3. So then these are the control limits, right? So then there's my X bar chart. I say, oh, damn, not all of this data was in control. The process was not in control. I had a problem in here. So I need to get rid of this data and then recompute my control limits. Okay. Now we also plot on a chart the standard deviations. So that is these guys here, right? The only question is, how do we calculate the upper and lower control limits, right? So the answer is we're going to use a chi-squared distribution because standard deviation typically, the behavior of standard deviation is that of a chi-squared, right? So we find for a sample of size 5, we can find the first percentile of the chi-squared distribution with 5 degrees of freedom, or the 99th percentile and the first percentile. And then we need to multiply these percentiles. What am I doing here? So Q3. So this is my average standard deviation, right? This is the average of all of these n columns, right? So it's 2.99. So then I take this percentile multiplied by S squared, right? Q3 times Q3, and I divide by 5. At any rate, this is the computation that gives me the lower and upper control limits. I'm sorry, after I take the square root, my bad. All right, it comes from this formula here that this statistic follows a chi-square distribution. So basically, you may or may not understand it. I explained it very poorly. At some point you learned about chi-square distributions and sample variances. This is how you set up the limits. So I set up my control chart. And indeed, you can see at least 2 points, if not this one here as well, that are way out of control that you eliminate and reset it up. But I did want to show one other thing. Because this sample data that I generated here, I generated it myself. And when I generated it, I put in a couple of things into it. First of all, I had the standard deviation to be equal to 3 throughout, except for periods 10 through 15. And I had the average to be 10, or the expected value to be 10, except for these periods here. All right? So fairly small changes in the process. But when you look at the control charts, you can clearly see the change in the mean. And you can also see the change in the standard deviation. It sticks right out, right? So whenever over here, this just shows the process changed, it's easily detectable in these control charts, right? So they actually work. They work very well in detecting anomalies in your process. All right, so that's how control charts work. It's how you set them up. And I think I'm pretty much done. Let's see what else I got here. So there's a little bit more to it. Sometimes people suggest you look for patterns in your control chart. So what you want to see in your control chart is pure random variation, right? Natural random variation. If you see any kind of patterns in there, then that's non-random variation. That's not natural variation. And that would cause you some concern and perhaps get you to try and figure out why this variation is occurring. So they look at things like it runs below the mean and above the mean, or runs up and runs down, various patterns like that. All right, so this is basically a process monitoring technique. Control charts are used to monitor the processes and detect non-random variation. Now the feedback part is not very strong. We've detected a problem. The feedback, the fix is basically says go fix it. So it's not necessarily telling us how to fix it. It's just telling us that there's a problem we should fix. So it's quite reactive in nature, right? It's not proactive. And if you were to study quality in any more depth, you would find that beyond simple statistical process control, there are design of experiments-based methods that are meant to be more proactive, run experiments on the process, and use the results of the experiments to try and minimize the variation. Okay, that is officially the end of this lecture. I see Michael is sound asleep on his pillow.
I'm not asleep.
I'm almost asleep, so it's okay. All right, so that's quality. And I'm done talking. If anyone has any, how could CDs sell all their stock and not crater in stock price? I do not understand that. I don't get it. Nobody's ever tried that before. I was shocked. All right. I guess that's it, Shachil. You can send them off.